Welcome back to Databytez, your source for data-driven principles. Today we are focusing back on the technical side of data with data structures. What are data structures and why are they important? So let's jump right in. So what are data structures? Data structures are organized and specialized ways to store, manage, and organize data in a computer so that it can be accessed and modified efficiently. They form the foundation for implementing algorithms and play a critical role in solving complex computational problems. So really, data structures are pervasive. Do not believe under the misconception that these solely belong in the realm of software engineering, because this is kind of where they go, and it's actually the bane of a lot of students' existence because data structures can be very difficult. And just to illustrate that, let's kind of look into the two flavors that data structures come in. We have the primitive and simple, and the non-primitive or complex. Now, the primitive is the kind of stuff that you probably are aware of, and you might not really give much thought to, which are integers, okay, whole numbers, floats, decimal numbers, characters, string, and booleans, true and false. Now, these are foundational. You probably not much think of it. You type a number on there, you're not really thinking that it's a data structure of any sort. But these are bits. At the end of the day, all of this is translated into bits, and the computer just recognizes everything as ones and zeros, on and off. But we need to conceptualize it in ways that we can understand. So, it's translated. Everything is going to machine language or binary. And it's going to eventually, on the screen to us, appear like, oh, it's just a 2, but it's like 10110, whatever it translates to. And as a result, floats are interesting, just kind of going a little off tangent here, but floats are a little bit interesting because of the fact that computers don't really deal with decimals. Everything is 1010, so they kind of have to do these weird things in order to get non-whole numbers. But again, primitive, not really super important. It's something that's kind of native to us and we don't have to think about. It's the non-primitive, the complex ones that we have to really wrap our mind around, and it can be a lot. And this list is not exhaustive, so what you see here is not every single possible data structure that exists. And even within the complex, there are two subtypes. There's the linear and the non-linear. So in the linear data structures, we have arrays, linked lists, hash maps, stacks, queues, heaps, and whatever else that exists out there. And then on the nonlinear, we have trees and graphs. And you might think, oh, this is a lot to know. And again, you're going to see it's not really, you don't really have to do this unless you're really going into software engineering. You really want to get into programming in that deep. You're really going to have to familiarize with yourself with all of this. But for most people, knowing just a few can really help you out a lot. You'll start being able to conceptualize problems differently. But I'm getting ahead of myself. Why are data structures important? So I've already kind of talked about this a little bit, but reason number one, problem solving. The right data structure can trivialize a problem. So, sometimes you're bashing your head thinking how you're going to solve something. Maybe a problem comes across and you're like, how do I solve this? And really it can come down to choosing the right data structure to tackle the problem. So here we can imagine we have people waiting in line. Now, I don't want to go too far into examining all the different data structures because we're going to do that separately. But you could, in theory, use an array to model what it's like waiting in a line. The problem is an array does not really hold order of the elements within it in the way something like a queue does. So you always want to ensure that there's a certain behavior being followed. The first person in the line is the first person who's going to get service. The first person who's going to go through the process, whatever that is. And you can ensure that with a queue because its behavior is supposed to act that way. An array does not ensure that behavior happens. So you might have to do extra work if you wanted to use an array to solve that kind of problem. And so choosing the right one can make your life a lot easier, just like choosing the wrong one can make your life a lot harder. And now, not all things are going to have the same kind of data structures available to them. For instance, if you're using a general programming language like C, Python, JavaScript, whatever, you're going to have access to a lot more variation. You're going to have a lot more data structures to choose from to tackle your problems, unless you're choosing a very closed system like Excel. Excel doesn't really have the same variety of data structures to your disposal. So sometimes you have to get a little bit tricky, because as we'll see later in this, as we continue this discussion in a separate video, there are multiple data structures, believe it or not, available in Excel. You can kind of model them using functions to kind of get the same properties that some of these other data structures have. So reason number 2, efficiency and scalability. What is efficient at one scale is inefficient at others. For instance, again, going back, an array might make sense if it's only 10 elements. That could be in an array at any given moment. This is because, again, a little bit extra detail here, an array usually has to reserve the amount of memory it is, and the memory is contiguous. I think that's how you say that word. Where it's the memory has to be reserved sequentially in the block that it's going to be in. So think about your RAM, right? Think about your RAM. And if you were to divide, let's say you have 32 gigabytes of RAM, each byte is a block, or each bit is a block, whatever. If you wanted to reserve 10 elements, you have to reserve 10 blocks sequentially. All the blocks need to be next to each other, and that is it. You have those 10 blocks. So if you wanted to have 11 elements in there, you have to kind of make a new array, because you only reserve 10, and the next block might be taken up by something else. So it will not work. So if you, at the most, you're going to need 10, and you might have 5, 6, 7. You're going to be wasting some of the blocks. You're going to be a little bit inefficient, which is okay at 10. But what if you had 10 million? Now you're reserving 10 million blocks when you're not really going to be using all of them all the time. That's kind of a waste. You would want something a bit more dynamic, something that, okay, I can take 10 million, but I don't necessarily have to reserve it. Maybe I can give those resources for something else that might require it. So scale always rears its ugly head, and it's really where scale becomes complexity arises. And so, of course, this also relates to the complexity of the data set you're working with. So even though it's kind of a file type, I want to include it in this conversation. So the normal way we transmit information is through CSV or Excel files, Excel workbooks. So none of that contains information. A CSV might not contain any information about the data type that describes the values that are in there. Excel might, but you have more complexity in Excel file because it's not a flat file, meaning there's multiple files actually inside an Excel workbook. And instead of just being comma separated values, it's actually encoded in what's called an XML file with all the metadata also included, like what kind of data type it is and whatnot. On the other hand, when you're dealing with APIs, it's not really efficient to transmit this information on CSV or an Excel file. It's just too much. It's too much to transmit for all the calls that are going to be made. So oftentimes what's used is a JSON, which stands for JavaScript Object Notation, which really looks like a hash map or a dictionary. And this offers two things. One, it's a lot more memory efficient, meaning it doesn't take up a lot of space relative to how much data is in there. It doesn't have to store metadata, just like a CSV. It's interpreted usually by the machine when you're using it. And the other thing is that it offers a lot more flexibility. It's not so rigid like a CSV, or unless I don't think it has the same flexibility as like a Excel workbook, it's still great. And that's why JSONs are referred to, or dictionaries are semi-structured, because it kind of follows a certain pattern, but it's not super rigid. And again, we're going to dive into that later, but just to highlight the fact that efficiency and scalability also play a role in choosing what kind of data structure you're going to use to work with the data. And finally, again, touched on it here, it's kind of pervasive, it's memory implications. So some data structures consume more memory and leverage memory in impractical ways relative to the problem. Again, highly tied to implementation, and really only becomes a concern with scale. Scale, it's always about scale. The bigger the problem you're trying to tackle, with more people dealing with the same resource at once, scale becomes a concurrent users, blah, 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 blah. If you're really into software engineering, that's going to be you're really going to be dealing with scale, because a lot of these big companies, have a lot of people to serve. But again, for most people, not really a big deal. Scale is not something you're going to really have to tackle. And it's more about just being aware that these things are concerns, but really the first one is just tackling the problem. It's, again, really trivializing a problem that could you really have your banging your head against the wall just by understanding what data types exist and what data structures exist, instead of trying to brute force your way through it. So, coming back to this, how many data structures should you learn? We didn't cover, but we saw that there were a lot of complex data structures. And really, again, this depends on where you want to go with your life. If you're going software engineering route, you really want to work in the tech field, you're really going to have to familiarize with all the data structures, because that's just what employers want. But for everyone else, the big three: arrays, lists, because they're kind of the same thing, just a little bit different in terms of the details. Hash maps, also known as hash tables, dictionaries, and I like to include here the n-dimensional array, and I like to distinguish that from just the normal array and list. And if you just learn these three, that solves 80% of the common folks problem. And these are the ones that I feel like I just see all the time appear for the most common things that you'll tackle. And again, unless you want to go the software engineering route, you got to learn all of them. You really got to familiarize with all of them. Different people use different ways to implement their solution. So anyways, that was the introduction to data structures, what they are, why they're important. Again, they just really make life a lot easier, just really knowing that. And again, we're going to cover that in a next video. We're going to be going through how these data structures repeat themselves in two different technologies. One being the programming language Python. We're going to really start seeing how arrays and lists and hash maps, these arrays, keep repeating in their appearance. They just get called different things, but it's all the same thing. And then we're going to look at Excel and see how it's mirrored in a very, very common language. Because again, Excel is a programming language. It has all the features that you need. Then it has these same things popping up over and over again. So, hope you enjoyed the lesson for today. Have a good one. Laters.